thanks to the organizers for inviting me. It's a great pleasure to be here. So my name is Sylvain Schwartz. I'm with Laboratoire Kastler Brossel in the group of Jakob Reichel. And before that, I was with Mikhail Lukin at Harvard. And today, I'm going to tell you about two experiments that are performed in these two groups. And these two experiments share in common the same goal of building large, controlled quantum systems with individual neutral atoms. Right, so because Jean-Michel Raymond gave a very nice introduction 2 talks ago about quantum technologies and quantum simulations, I will make mine quite short. So I just wanted to remind you that there exists a bunch of possible physical implementations of elementary quantum systems, be it real single particle systems like neutral atoms or ions, or artificial systems behaving like single particles. And all these possible systems have in common 2 goals. One is scalability, namely you want to bring together as many of these elementary systems as possible, and controllability, namely you want to do this while maintaining a high degree of control over each individual system. Right, and today I'm going to advocate for neutral atoms as a nice candidate for building these elementary control systems. Neutral atoms have some obvious assets, such as long coherence times. Think about atomic clocks, for example. They are relatively easy to manipulate thanks to the well-developed toolbox of AMO physics, and they're intrinsically indistinguishable, which is a strong asset in this context. And of course, if you want to use them for quantum simulations, for example, you have to address some challenges. One of them is how to control individually the atoms within larger systems, and another is how to create interactions between them. You need interactions to create a quantum entanglement. Otherwise, it's boring. Right, so the approach in this talk is to build these atomic systems by using neutral atoms with individual control and imaging. I'll tell you how in a second. And then to engineer some desired Hamiltonian by adding the extra ingredient of controlled interactions across the array of individual atoms. And with these two, by mixing these 2 ingredients, I hope you will be convinced at the end of this talk, if not already by Jean-Michel Raymond's talk, that what we get with this approach is a versatile platform for quantum simulations and quantum technologies in general. Right, so here is the outline of my talk. I thought it would be nice to start with a very short tutorial on cold atoms, because probably not everyone in the audience is expert in this field. And then I will move on to describing these 2 experiments I've talked about. So the Rydberg atom array experiment performed in the Lukin group, and the register of single atom with cavity-mediated interactions performed in the Reichel group. Right, so let's start with cold atoms. So how to cool down and manipulate atoms. So basically, one has to recall that in this context, the temperature of the atoms is related to the average quadratic velocity of the atoms. So by cooling them, we kind of make the quadratic average velocity very close to 0. And the basic principle to do this is first, you have to understand how to create a force on the atom. And to create this force, what you use is radiation pressure. So imagine you shine a laser light on a 2-level atom. The atom will absorb photons from this laser beam, from which it will get some recoil. And this recoil will always occur in the direction of the laser beam. And then the atom will re-emit this photon in a random direction, for which it will get another recoil, which is in a random direction. So after many cycles of absorption and emission, the momentum due to absorption adds up along the axis of the laser, while the momentum due to the spontaneous emission average to 0, and so you get a net force, like your laser pushes the atom in the direction of the light propagation. So that's how you create a force. Now, how do you cool the atoms with lasers? Well, first assume that a 1D problem along one axis. So obviously you need two lasers counter-propagating on the atoms, but if you do this on resonance, nothing happens because the force induced by the two laser beams will cancel out. The net force will be 0. So the extra trick is to tune these lasers out of resonance with the atoms at rest, such that when an atom has a velocity is moving in one direction, because of Doppler effect, it will be more resonant with the laser beam pushing it to the opposite direction and vice versa. So this is how you create a friction force, but because it involves Doppler effect, the net force in the end is proportional to the velocity of the atom, so this is the equivalent of a friction force. And this is not enough. To trap the atoms, you also need a restoring force, something that acts like a spring. And for this, you have a similar trick, but which is now based on a magnetic field gradient. And you count here on the Zeeman effect, which tells you that the atomic frequency will depend on the strength of the magnetic field. And so if you put a gradient, you can put yourself in a situation where when the atom will be to the right of the 0 of the magnetic field gradient, it will be pushed to the left and vice versa. And this acts as a restoring force because it is not proportional to the position of the atom in the magnetic field gradient. So by combining these two ingredients, what you get is a magneto-optical trap, which is the kind of basic ingredient for called atom physics. And then usually what people do is, at least some people, is to transfer these atoms from the magneto-optical trap into a non-dissipative trap in a second step to get rid of the noise associated with spontaneous emission from the magneto-optic trap. And for this, you have basically two possibilities. Either you act on the magnetic dipole or on the electric dipole of the atoms, which will be trapped either in a like minimum of the B field or minimum of the electric field. So here's a movie I like a lot from the company called Quanta, which just gives you maybe a visual impression of what it looks like. So here the atoms are first cooled in 2D, and then the beam is used to load atoms in 3D, which are then transferred into a purely non-dissipative trap. So here it's a magnetic minimum created by a microcircuit or atom chip, as described by Jean-Michel Raymond before. And here what is shown is evaporation, where you throw away the hottest atoms to get a very cold and dense sample in the end. So in the experiment I'm going to describe here, we use the other approach, which is to trap the atoms in electric fields. So the ingredient here is called an optical tweezer. So basically, it's a laser beam, which is tightly focused and off-resonant with the atoms, such that the atoms are now see a light shift coming from this laser beam. And if you choose the right detuning with respect to the atomic transition, you can put yourself in a situation where the atoms are attracted by the maximum of intensity, so they will kind of accumulate at the focus of the laser beam or optical tweezer here. And it was demonstrated in seminal experiments by the group of Philippe Grangier in 2001 that there can be a regime where there can be, when you load this optical tweezer from an optical molasses, so a sample of cold atoms, as I have described before, you can put yourself in a regime where there can be at most one atom per trap. So this regime is called the collisional blockade regime. So the two ingredients are very strong confinement of the optical tweezer. So usually you use a huge high numerical aperture objective to really focus your tweezer down to an area of 1 micron cube, typically. And you also need these extra cooling beams that you would use in a magneto-optical trap, which induce what are called light-assisted collisions. And the result is, as soon as there are two atoms in the trap, they encounter losses which kick both atoms out of the trap. So at the end, you get either 0 or 1 atom in your optical tweezer. And this is a stochastic process. You cannot control whether you'll get 0 or 1. And that's a very important ingredient for what follows, because now we have a tool to isolate and manipulate 1 atom per optical tweezer. And this brings me to the first experiment I wanted to describe today, which is this array of Rydberg atoms performed in the Lukin group. So here, the approach is to start with an array of typically 100 of these optical tweezers, which are in this collisional blockade regime that we load from an optical molasses. And the idea now is to make an image of the atomic distribution after some loading time, and to use the information contained in that image to turn off the empty traps. Remember, it's a stochastic process. But because we can image them, we can know which trap is empty, turn it off, and then rearrange the other traps to create a defect-free array of single atoms before turning on interactions in the form of Rydberg dipole interactions as described by Jean-Michel before. All right, so how does this work? A little bit more concretely. So at the heart of the device is an acousto-optic deflector into which we send typically 100 different tones, and each of these tones will create a diffracted beam with a different angle, the angle being dependent on the frequency that you send into this AOD. And then these beams are imaged through a high NA objective to form an array of traps at the center of a vacuum chamber here. And then we create a MOT, send an optical molasses, wait for some loading time, then send some cooling beam to make the atom fluoresce. And the fluorescence is collected through the same high NA objective here back to a CCD camera, which gives us an image of the atomic distribution after the loading. And then we use this image to apply some feedback on this AOD. So basically, we remove the tones corresponding to the empty traps, and we change the other tones to move the atoms into the desired configuration. So here is typically what we get. So the first line here is the array of traps. So this is just the image of the 100 optical tweezers on the camera. And then we start with a randomly loaded array. So here's one randomly single-shot image of what we typically get. And after the rearrangement, we can get, for example, a defect-free array of on the order of 50 atoms. But it's not the only thing we can make. We can make, for example, clusters of 2, clusters of 10, or basically any arbitrary configuration in 1D you can think of. And these are superposition of 1D images. It's not 2D image, don't get me wrong. All right, so the takeaway message here is that we can make large arrays. We have a relatively fast cycle time, so we can repeat the experiment 4 times per second, typically. I'll show you a real-time movie a bit later in the talk. And basically, we can build any arbitrary arrangement in 1D with one constraint that the minimal distance between 2 atoms cannot be made smaller than a few microns, like 2 microns typically. And because at 2 microns, neutral atoms typically do not interact, we need to add an extra ingredient, which is Rydberg physics, which was, again, nicely described by Jean-Michel before, so I'll be fast on that. But basically, when you couple an atom to a high value of the quantum principal number, this gives the atom some exaggerated properties, including long lifetimes and strong dipole-dipole interactions. So here we restrict to low L level in these experiments. And in particular, these dipole-dipole interactions can be as a dominant energy term up to 10 micron, which is typically a few sites across the array for n equals 70, which is our choice of principal quantum number. All right, so in practice, we couple the ground state atoms to a Rydberg state with a 2-photon transition using some intermediate level. So by shining 2 counterpropagating laser beams along the axis of the atom array. So the idea is that all atoms see the same Rabi frequency coupling the ground state to the Rydberg state. So they are globally excited. And typically, the Rabi frequency we get with the available laser powers are on the order of 1 to 10 megahertz. And because the Rydberg atoms are not trapped, so they do not feel the trapping potentials, they are actually anti-trapped by the tweezers. That gives us a convenient way of detecting them as missing atoms. Basically, what we do is we first create the array, we turn off the traps, do the physics by shining the Rydberg lasers, and then turn the trap back on. And any missing atom, we attribute it to being excited to Rydberg, and then it's not recaptured by the tweezers when we turn the traps back off. So everything happens in a few microseconds. So what you see here is a typical example of Rabi oscillations between the ground and Rydberg states, in the case of a single atom. So we typically have a few seconds, a few microseconds, sorry, coherence time. And because these interaction times are so short, it is safe to neglect the atomic motion on this time scale. And we are left with what was again introduced before by Jean-Michel, which is a frozen Rydberg gas Hamiltonian, where we have only 3 relevant terms in our case, which are, so again, this global driving between the ground and Rydberg with the lasers, which can be changed globally by changing the laser intensity. Then the detuning of the Rydberg lasers with respect to the transition frequency of the atoms, which can be, in principle, controlled at the single atom level by inducing extra light shift on individual atoms. I'll show you how in a moment. And we have this interaction term, which can be controlled either globally in our case by going to a different principal quantum number, or locally by playing on the distance between Rydberg atoms, which we can do relatively easily with our setup, as I explained before. All right, so what can we do with this? So the simplest physics, which was again introduced by Jean-Michel before, is this so-called Rydberg blockade physics. So very quick reminder, when we drive oscillations between ground and a Rydberg state, atom and when we put 2 of these atoms together, when they're far apart, then you can go from the doubly ground state to one of these states where either the left or the right atom is excited to Rydberg, to this doubly excited Rydberg state here. But as the atoms get closer and closer, the doubly excited state moves away from resonance with the laser. And at some point, if you start from the ground states, which we'll do in the experiment, it is safe to neglect the doubly excited state. So you can remove it completely from your Hilbert space. And then you're left with the remaining dimension 3 Hilbert space, which is usually convenient to rewrite in terms of the symmetric and anti-symmetric superposition of these states having Rydberg excitation either to the left or to the right, and plus, of course, the double ground state. And when you compute the matrix elements between the ground state and this bright and dark states here, well, you find 0 for the anti-symmetric superposition, which is called dark, and you get √2 times the single atom Rabi frequency for the bright state. So at the end of the day, you're left with a very simple system, which is just a 2-level system between the ground, many-body ground state and this symmetric superposition of states where one Rydberg excitation is shared between the left atom and the right atom with a √2 enhanced Rabi frequency. And interestingly, this can be generalized to the case of n atoms as long as they all sit within one blockade radius of each other. And this we could, so we are not the first one to check this, but we could check this as a sanity check very nicely in our system by going to clusters of 1 atoms here. Here, in the first line, the atoms are far enough that they do not interact with each other. So basically, we perform many single atom experiments in parallel, and we see these first Rabi oscillations here between the ground and Rydberg. And then we can make clusters of 2 and clusters of 3, which are fully blockaded. And what we see are, again, nice Rabi oscillations, which is a signature of 2-level physics, with this enhanced Rabi frequency of √2 and √3 here. And of course, we have tried to do this for more atoms, but in our case, the blockade radius is on the order of 3.5 sites. So as long as we go to more atoms, we can still try to fit some sign function to the results, but we kind of deviate for this ideal √n dependence, which is, again, which you can only hope for when in the fully blockaded situation. Okay, so here we can pause and think again that this nice Rabi oscillations here occur between the many-body ground state and this W state, where one Rydberg excitation is now shared or delocalized over all possible sites of the array. All right, so now we have used this to characterize the fidelity of the preparation of this W state in the case of two atoms. And so what we do here is we just perform this Rabi oscillation. So now we take two blockaded atoms and we drive them with a resonant light. And so what we do is stop after a pi pulse, after the first oscillation here. And when you stop here, ideally you prepare this symmetric superposition of ground Rydberg plus Rydberg ground over root 2, which is an entangled state. And now we can ask ourselves, what is the fidelity of the preparation of this state? And for this, of course, one needs to measure the populations of the state that we have prepared, but also the coherence between the between the bright state here and the dark state. Sorry, the coherence of the non-diagonal elements of the density operator of the W state that we have prepared. And a way to measure this coherence is to use some single atom addressing thanks to an extra laser beam, which only talks to one of the two atoms and which just induces some light shift, which will add a phase shift here. And then the procedure to measure the coherence is just to first do a pi pulse starting from the two-atom ground state to prepare this superposition, then apply this single atom light shift, which now induces some oscillations between the bright state and the dark state here by adding this light shift. And then, after some variable time, we do another pi pulse to couple the bright state to the many-body ground state here. And when we plot the population of this many-body ground state after this procedure, it can be shown quite straightforwardly by writing the density matrix that the oscillation, the amplitude of this oscillation of the population of the many-body ground state here, when we vary the phase accumulation time due to this extra beam. So the contrast of these oscillations is a measure of the coherence of the W state here, the non-diagonal elements of the corresponding density matrix. And with this, we could show by correcting also for detection infidelity, which is not 100% in our case. So detection infidelity is marked by these gray dashed lines here. And you see that we get very close to the limit imposed by this detection fidelity. So by correcting from this, what we get in the end is an entanglement fidelity of 98%, which is limited by the residual effects like spontaneous emission from the intermediate state and a limited lifetime of the Rydberg state. All right, so now we have some kind of high fidelity control over this array of Rydberg atoms. What else can we do with this beyond trivial blockaded physics? So for this, let's go back to this Hamiltonian. So things becomes quickly quite complicated because this is a many-body physics. So maybe to take an extra small step, let me consider the case where we have only 3 atoms and to see all possible states that we can get with this Hamiltonian. So for extra simplicity, let's first assume that the Rabi frequency goes to 0. So I'll switch this back on at the end. And so we're left with 2 terms in our Hamiltonian. One is a detuning term, which in this case can be seen as a chemical potential, or in other way, it tells me what is the price, what is the cost in energy to add 1 extra Rydberg excitation in my system. And this price can be either positive or negative, depending on the detuning. And the other term, the interaction terms, tells me the price, again, that I must pay to put 2 Rydberg excitations at some distance, or ij, from each other. And this price is always positive. These Rydberg van der Waals interactions are always positive. C6 here is a constant positive coefficient. All right, and now I can plot the energy of all the ground states of this, all the eigenstates, sorry, of this Hamiltonian as a function of the parameter delta here. So I have first a state where all 3 atoms are in the ground state, which have 0 energy. I can put 1 Rydberg excitation, which gives me a minus delta slope in this Hamiltonian here, and no offset because there's only 1 excitation. I don't have any interaction term. I can put 2 Rydberg excitations next to each other, but this costs a huge price. As we told before, the distance here is such that we're in this blockaded regime, which means it costs a very high price, or this interaction term here is very high. So this gives me a minus 2 delta slope here, and a huge offset V here, which is much larger than any other energy scale of the system. But of course, I can make this V much smaller now if I put my two Rydberg excitations away from each other. Here, by putting the two Rydberg excitations on the edge of this 3-atom cluster, I have divided here V by 64 because I have made the distance twice bigger, but because this goes to the power 6 of the distance, now V is reduced by 2 to the 6, which is already quite significant physically. And to be completely exhaustive, I must also consider the 3 Rydberg excitation case, which has a 2V offset and a -3 delta slope. All right, so here are my eigenstates. Now if I put back the driving term, so which is this Rabi frequency omega, all these crossings here becomes anti-crossings because of the coupling. And in particular, if I zoom here, I see that there is now a possibility to deform the ground state of this many-body Hamiltonian from this state here, where all atoms are in the ground state, to this ordered state where I have one Rydberg excitation, one ground state atom, and one Rydberg excited atom again. So this is for the trivial 3-atom case. And now to go further, we must rely on theorists. So there was a study of this model by the group of Subir Sagdev from Harvard University in 2004, which came out with some phase diagram of this Hamiltonian, where again you vary the detuning along the x-axis, and you vary the interaction strength, so this C6 coefficient, for example, over R6, along the y-axis. And what we do here, in the case of some moderate interaction range, we recover this Z2 order phase, where every other atom is excited to Rydberg. But as the strength of interaction increases, the blockade radius becomes larger and larger, and then the phases that come out of the simulations are Z3 or Z4 order, where you get one Rydberg excitation every third side of the lattice or every fourth side, etc. So this is theory. Now the good news is that we can probe this phase diagram with our experimental system, which can be seen as a quantum simulator in this case. And for this, what we do are detuning sweeps starting from the many-body ground state here into these ordered states. And this is what it looks like for the Z2 ordered state. I think Jean-Michel showed this picture in the talk, so I'll be fast on there. But basically here we have a 13-atom cluster. This is how it looks like. And when we do this sweep towards large positive values of the detuning, at the end we create this Z2 order phase where every second Rydberg atom is excited. Every second atom, is excited to Rydberg. All right, and then we can change the interaction strength by changing the distance between the atoms. We just make them a little bit closer, which increases Rydberg interactions, or to use fancy words, we kind of have a programmable quantum simulator because we cannot change this parameter here, interaction strength, and we can do a sweep into the Z3 order, where you see now that every third atom is excited to Rydberg, and we can play the same game for the Z4 order there. All right, so now the next question is, how good are we at preparing these ordered states of this phase diagram? And for this, we kind of now concentrate on sweeps into the Z2 order with the largest kind of possible size that we have experimented with so far, which is a 51 atom array. So when I do sweeps into the Z2 order, of course, ideally, I would expect to get a Rydberg atom every second side of the lattice. So here, Rydberg atoms are, remember, detected as missing atoms. So I've just marked them with red circles to kind of show that there is a missing atom, which we attribute to Rydberg. And what we get, of course, is not a perfect anti-ferromagnetic chain or alternating chain, but rather some anti-ferromagnetic chains separated by defects, which are squared in blue here. And of course, a different shot of the experiment will give you a different picture here. And these defects are called domain walls. In this context, they can be seen as walls separating anti-ferromagnetic or anti-ferromagnetic chain of perfectly alternating Rydberg and ground state atoms. And this is convenient because now we can perform, again, the experiment many times and count the number of domain walls as a kind of matrix to quantify how good we are at preparing these states. So remember, all the atoms in ground state will be a domain wall density of 1, because each atom is a domain wall in this case. And a perfect antiferromagnetic chain would be a domain wall density of 0. And as we do the sweep, and we average over many instances of the experiment, indeed we see something going from 1 to something which is close to 0. And if we look at the variance of this, we see also a peak at the position of the phase transition, which is compatible with, again, theoretical description of a quantum phase transition as we sweep into the Z2 order. All right, so now how good are we at preparing this state? So to do this, what we have performed is what we can do is repeat the experiment many, many times, typically 10,000 times, and count for each instance how many domain walls you get. Ideally, you want 0. And then you can plot the histogram of how many domain walls you've gotten after performing 10,000 times the experiment. And you see that it looks like that. And this is mostly dominated by imperfections in the detection. So I've been quite fast on this so far, but remember, we are detecting a Rydberg atom as a missing atom. But for example, a ground state atom could be kicked out of the trap due to collisions with a residual background gas. And then we would count this as a Rydberg atom while it is a ground state atom. And conversely, a Rydberg atom could decay because it has a finite lifetime. It could decay back to the ground state and be recaptured by the traps. And so that would be a false positive. So we have false negative and false positive. But we can characterize them very well. And so from this kind of histogram, we can use a maximum likelihood reconstruction algorithm to compute a parent distribution given the known limitation in our detection fidelity. And this gives you a kind of ultimate fidelity, which is on average 4 domain walls in a chain of 51. And this we attribute to not being perfectly adiabatic and spontaneous emission during this adiabatic sweep. We have to make a trade-off. To be perfectly adiabatic, we would have to be infinitely slow, but then we would be hit by spontaneous emission from the intermediate state, so we cannot be infinitely slow. And so there's a trade-off which leads to this 4 domain walls. So is it good or bad? Well, it's a matter of appreciation, but what we like to show is another way to plot our data, which is now, so for 18,000 instances of the same experiment, we get, for each instance, we get 1 microstate, which is a single-shot image like that, and we can count how many times we got each microstate. So remember, there are 2 to the 51 possible microstates, which is a huge number. So most of them, we don't observe them, of course. Almost 80,000 of them we observe once. But there are some specific microstates that we observe twice, 3 times, 4 times, etc. And if you plot the data in this way, you see that there is 1 microstate that stands out of the others as being observed 20 times out of 18,000. And this microstate is the perfect antiferromagnetic chain. So in other words, the system kind of, in spite, even with the experimental imperfection, the system can isolate here the ground state of the experiment with high fidelity, which is kind of promising in the spirit of doing this quantum optimization algorithms, where you rely on this kind of adiabatic sweeps to find the unknown ground state of a many-body Hamiltonian. Of course, here the ground state is trivial, so it makes things much easier, but still it's an encouraging sign in this direction. So here's a real-time movie. So first line is a random distribution, second line is the initial state after rearrangement, and third line is what we get after the sweep. So you see we typically have 4 cycles per second, and then we just take. So this 18,000 data were taken over 2 or 3 hours. That gives you a time scale of the. It's not too painful in this sense. And of course, this movie ends on the perfect antiferromagnetic chain, as you would expect. Yeah. Anyway. OK, so no, that was for the static dynamics. So let me now move to some non-equilibrium physics that we've performed with this system. So the idea now is to prepare some Rydberg crystals, so still this alternating pattern of Rydberg and ground state, which we do by frequency sweep across the resonance here. And then once we prepare the crystal, so this is a crystal in the 5-atom case, what we do is a sudden quench, which means we set back the frequency of the Rydberg laser back to resonance, and we see how the system evolves. And what we see in this case are some oscillations between the initial Z2 ordered state and the complementary state where the Rydberg state has gone to ground and the ground state has gone to Rydberg before coming back to the initial state. And these oscillations are quite robust. They seem to be independent of the system size. And also, if you look at the frequency here, it's always kind of a similar frequency, which is on the order of omega divided by √2, where omega is a Rabi frequency. And these oscillations also persist for very large systems, as shown here by the oscillations of the domain wall density for 51 atoms in blue. You see that it's very similar to the 9-atom case. So we're a bit surprised by these oscillations, which are quite robust and seem to persist, to decay quite slowly with respect to the other time scale of the systems. So to understand more, there has been some theoretical simulations by Hannes Pichler and Soon-Won Choi from Harvard, who have shown that they could reproduce these robust oscillations by starting from the Z2 ordered state and considering only the constrained Hamiltonian. So remember, we cannot have two Rydberg excitations next to each other. This is a Rydberg blockade. And now, if you take this constraint into your Hilbert space, which means you remove all states which have two Rydberg excitations next to each other, then you let your system evolve in this new reduced Hilbert space. You get some constrained dynamics, and by putting this into the simulations, indeed, these oscillations were reproduced just with this constrained Hamiltonian. Now, starting from the ground state, instead of starting from the Rydberg crystal state, the oscillations were not observed. They were observed to decay fast as expected. And now, by looking at the full Hamiltonian, they could also predict that the damping of the oscillation is mostly due to the next nearest neighbor interactions. So basically, if you have just the constraint dynamics, it means you only consider interactions between nearest neighbors. That gives you the long oscillations in dashed blue here. And if you add now the next nearest neighbor interactions, which are quite weak, but still, these are responsible for the decay of these many-body oscillations. All right, so we're not exactly sure of what was going on in the system because it's far from any integrable system. There is no disorder. It's not many-body localization effect. But still, we have these robust oscillations, which are, we know this from the simulation, associated with the constrained dynamics due to the Rydberg blockade. And there was a theory paper published a few months after ours, which attributed this to quantum many-body scars, as they say, which are kind of some states which are embedded throughout the many-body spectrum, which is thermalizing, but only these states exhibit some robust dynamics. And in our particular case, these two order states is one of them, which is why, according to this paper, we show these many-body dynamics, which they kind of attribute to some new kind of universality class of many-body dynamics. So anyway, that's for the new physics that we could observe with this many-body dynamics. Now I wanted to also point out that this can be a tool more in the spirit of quantum technology and building large GAG or entangled state. So I'll tell you how with this simple example of a 6-atom cluster. So now I'm considering an even number of atoms. So far I've considered only odd atoms because with odd atoms the ground state is trivial because we have two Rydberg excitations pinned on the edges, and then you can fill the lattice with one Rydberg excitation every second side of the lattice, and at the end you end up also with a Rydberg excitation at the other edge of your crystal. So in this sense, the ground state is non-degenerate. You have only one ground state. Now if I go to even number, it's a bit trickier because I have two degenerate ground states, which are illustrated here. So as usual, it is energetically favorable to put Rydberg excitations at the edges of the crystal, but then I must pick up one atom from the middle excitation, and now you see that you have two energetically equivalent configurations. So what happens if now I take this and make an adiabatic sweep through the quantum phase transition? So I can, here are single shot images reproducing these two configurations, and I can plot here the many-body population that we have observed after performing this sweep several times. And you see that indeed the two kind of most often observed states are these two states, 100101 and 101001, corresponding to these two guys here. But of course the question is now, what do I have prepared? I have prepared a quantum superposition of these two many-body states, or a statistical mixture. And this is not so easy to tell. We could, of course, do the full quantum tomography of the state, but this scales very badly with the system size. And that's where the quantum many-body dynamics might be an interesting new tool. And to illustrate this, so I show you this preliminary data where we have prepared this kind of unknown state where we don't know whether it's a statistical mixture or a quantum superposition of these two 6-atom states. And now what we can do is perform a quantum quench as before and look at the many-body dynamics over time during the quench. And because it's only 6 atoms, we can do the full simulation. And so we can compare our experimental data, which are the dots here, to the numerical simulations on two scenarios, one with statistical mixture and one assuming a quantum superposition as the initial state. And, well, with a bit of generosity, you might agree with me that the second data agree more with the theory than the first one, which could be a good sign that we have prepared something which is close to a superposition. Of course, I'm not claiming that this is a rigorous proof, but that is to illustrate how this quantum many-body dynamics could serve as a new tool as a proof of entanglement in many-body systems, where full tomography becomes exponentially difficult. So now to go further into this direction, there is an ongoing collaboration between the Harvard team and the team of Tommaso Calarco on optimal control algorithms, which could serve, in this case, to prepare larger entangled states. The idea here is that you don't have to do an adiabatic sweep. You can, of course, you have full control over omega and delta, which are the two parameters. So you could use more clever way of doing this, and that's exactly what they are doing now in the Harvard experiment. And these dynamics after a quench could serve as the indicator that optimization algorithm could optimize on to generate this quantum many-body entangled states. And of course, the high experimental cycle here is an asset, an obvious asset for the smooth running of such algorithm. Right, other directions in the group include the probing of critical exponents at the different phase transitions into Z2, Z3, and Z4, and relating this to the dynamical behavior as we cross the phase transition with various speed. And there are some predictions known as Kibble-Zurich, where this prediction relates the size of the domains as a function of the speed to the critical exponents, so the static exponents associated to the phase transition. So this is something we can naturally probe with these systems. Of course, there are ideas to scale up these arrays to 2D or to get more individual control by adding more single addressing beams. So far, we have only one. And in the long term, this platform could be nicely suited for quantum approximate optimization algorithms. Wow. All right. That was a nice transition to the third part of my talk. Everybody's okay? Okay, well, don't see any smoke. Okay, let's go on. So now, in the last 5 minutes, I wanted to quickly introduce you to another experiment which is currently being built in the group of Jakob Reichel at ENS, 5 minutes walk from here. And here the idea is still to have 1D chain of single atoms, so use this collisional blockade regime to get at most 1 atom per trap. But instead of using many optical tweezers, here we use an optical lattice, which is sustained by a Fabry-Perot cavity. And this Fabry-Perot cavity also serves as a way to generate interactions between the atoms. So remember before we used Rydberg physics to generate interactions. Here's a way to make the atoms interact is to have them coherently exchange photons through one mode of the cavity. And on top of that, we have put a high NA lens, which acts as a quantum gas microscope. So again, a tool to make single site imaging and addressing of the atoms. All right, so the cavity is a nice, like entangling devices as you can. If you put yourself in the strong coupling regime, 1 atom coupled to the cavity is enough to block the full transmission, and which means that as you measure the transmission of the cavity, you can differentiate between the state where all the atoms are in the, say, 0 state of the 2-level state here, and any other situation where at least 1 atom is in the 1 state. So as long as there is only 1 atom in the state 1, this will block the cavity transmission, and it will transmit only if all the atoms are in 0. And so the Reichel group has used successfully this technique to prepare large entangled states. So here, such as this large W state here, where again, so it's not excitation here, but it's just going from 0 to 1. So where one level atom is shared between all the atoms, so W state of this form. And they could do this by 2 different techniques. One is just to slightly excite the system with a microwave and then perform a measurement. If the measurement is that the cavity is transmitting, it means we're back to the 0, 0, 0, 0 state, and then we redo the excitation and measurement again. And as soon as we measure that the cavity is blocked, then with a high probability, it means that there is only 1 excitation in the system because we have made a very small excitation initially. And because, of course, there is no way to tell which atom has been excited as a final state is, to a very good approximation, this W state. And they could prepare the same state by doing quantum xenodynamics, where they start from all atoms in 1, and they keep measuring the 0, 0, 0 state, which is, again, measuring the transmission of the cavity. And then they perform some coherent drive of the system with microwave fields again. And because they keep measuring in 0, the system cannot reach the 0, 0, 0 state. And at some point of the coherent evolution, it reaches a state which is, again, very close to this W state. So this is our previous work from the Reichel group. And this is all based on this very successful technique that was invented at LKB, which is to use the tips of optical fibers as mirrors. So the way they do this is they etch the end of the fiber tip with a CO2 laser, and this kind of drills a kind of dip in the fiber tip, which is then coated and acts as a mirror. So when you put 2 of these fiber tips on top of each other, you get a Fabry-Perot cavity, which has a very small mode volume, and this is extremely favorable to get strong coupling between the atoms and the field of the cavity. And with this, they could achieve very high single atom cooperativity on the order of 100, which I think is the world record or close to the world record. Anyway, extremely high. And so that's basically the workhorse of the team to perform cavity QED with these systems. And now the new experiment we're building is based on a multi-mode fiber cavity, which allows to make a high-finesse Fabry-Perot cavity for 2 wavelengths at the same time. One is a 780, which is used for the coupling between the 2 levels of the rubidium atoms. And the other is exactly 2 times 780, which is used for the trap. And the idea here is to trap the atoms at some positions where they are maximally coupled to the 780 mode. So they all interact with equal and maximal strength with the cavity mode. So that's the kind of trick we're implementing now. And this is what, so the system is currently being built. So this is what the cavity looks like now. So here the cavity, the 2 fiber tips are here, the cavity is here. And on top of that is this huge aspheric lens. Well, huge, it's 1 centimeter width, but it has a very high numerical aperture to collect light from the atoms here and to be able to perform single-site imaging and addressing of the atoms along the axis of this cavity. All right, so where are we now? So we start from a motte and we transport with an optical tweezer the atoms from the motte into the fiber cavity. So these are images of the atoms climbing up to the cavity. These are the two fiber tips. And with this, we could probe the cavity and observe this vacuum Rabi splitting when we scan the frequency as a function of the cavity atom detuning, which is a good sign that we're in the strong coupling regime. And thus the next steps are to implement cooling inside the cavity to make the atoms fluoresce and be able to image them without destructing them. And then implement some physics with that. So one possibility would be to implement some Dicke Hamiltonian, so another artificially engineered Hamiltonian with Raman beams that we could again program by playing on the parameters of the Raman lasers, and which could also probably benefit from optimal control algorithms, even though it's not completely clear how at the moment. All right, so with this, let me finish with a quick summary of this presentation. So we have built defect-free arrays of atoms interacting through Rydberg states. We have observed some non-equilibrium quantum many-body dynamics with this. We could prepare with high-fidelity many-body states by sweeping through the across quantum phase transitions. And I have also introduced you to this register of single atoms in a fiber cavity, which is currently being built. And again, both of these single atoms, highly controlled systems, could benefit from control algorithms in the future by playing, for example, on the Rabi and frequency and detuning for the Rydberg atom array, or on the parameters of the Raman beams for the case of the fiber cavity. But of course, any idea, especially for this last point, are open to discussion and welcome. With this, I would like to thank the team, especially the experimentalists that we show here, the Harvard team, and here the ENS team. And to finish, I would like to thank you for your attention.
So, are there questions? Yeah.
I'm pretty loud, so thanks for this very nice talk. I have a few questions on the different parts. So, on the part about measuring the entanglement fidelity in the two atom Rabi flopping, you mentioned that in an individual Rabi flop, you don't have to worry about the temperature because it's much shorter than the time that the atoms move. But when you're doing this, putting on the light shift on the single atom and the phase, there's some time in between there, and then the bright and dark states would generally couple to one another through the Doppler shift, right? There's a phase, the atoms are moving.
Yeah, so
how much does that affect your...
So that's a good point. So there is definitely a finite temperature, which leads to a Doppler distribution. So the argument about this frozen gas is that this, say, the velocity of each individual atom and the position will not change over the few microsecond course of the experiments. But still there is a distribution in position and in velocity. So the distribution in position first adds you an extra, say, phase shift, which is like EI, K, XI, where XI is the position of each atom. So when we say we prepare the W state, it's in the sense of a W state with this, where these phase factors are included in the definition of the W state. So it's true that for every repetition of the experiment, we prepare a different W state, where these EI, K, XI factors are different. But because they don't change over the course of the experiment itself, which is a few microseconds, we have decided to we can define, it's at least safe to define this W state like this. And this is...
My question really is about...
And about the Doppler shifts now?
My question is, it's not really a criticism, I'm just wondering how much of the infidelity is not in the creation, but in the detection. That is to say, when you try to measure the off-diagonal element,
yes,
there's going to be an error. And so actually fidelity might be higher than you're claiming because you're introducing phase errors during the time
Yeah, so these Doppler shifts, they can be seen as random detunings, if you want, which are kind of relatively small compared to the Rabi frequency, but there are still, I mean, definitely an issue, and probably one thing limiting the fidelity, this 98%. Part of it is probably due to this random Doppler shift. Now about how we characterize, I don't think this affects the characterization, because when you kind of compute this parity oscillation thing, so you do a pi phase shift. So yeah, maybe, sorry, what I haven't mentioned in measuring this fidelity is that we implement some spin echo procedure on top of that. So we first do the pi phase shift, then we add this extra, you know, detuning to the left atom, which couples the bright and dark state. But then after some time, we make a 2 pi phase shift to exchange the role of left and right, and we let the stem evolve for the same time. And because these Doppler shifts are constant over these few microseconds, at least that's the assumption, but I think that's a safe one, these Doppler shifts cancel out, and that's how we get, I mean, such high fidelity. So but we just get rid of the effect of the Doppler shift on the measurement procedure, but the remaining 2% that are missing could well be also coming from the detection. Yeah. So in this sense, this 98% is a kind of lower bound on the fidelity. Yes, I agree. It's a fair point. Yeah.
Can I ask another quick question? Yeah. So
You're the chairman.
On where you measure the quench dynamics,
Yes.
You were saying that I missed maybe one central point. There was the theory in the constrained Hilbert space that was able to reproduce some of the sustained oscillation. So is that something, is there new physics there that is unable to be modeled in the system, or were they able to reproduce through the simple models
yeah, so
basically the essence of what was...
So no, it's, so to reproduce fully the observations, they need two ingredients. This constraint dynamics alone would give you even more robust oscillation, more robust than what we observe. And to kind of reproduce also this decay time, they had to include the next nearest neighbor interactions. So your basically nearest neighbor is infinite. You just remove this state from the Hilbert space. And then you add interactions between next nearest, so second neighbors. And this kind of induces a decay, which now matches quite well the experiment. So with this, well, at least with 25 atoms, where you could do this full simulation, the dynamics is pretty well reproduced. Now there was this theorist, interpretation of how to understand this in terms of many-body dynamics, classification, and so on, which is another question. But what we observe is, yeah, has been fully reproduced, at least in the 25 atom case.
More questions? No? And if not, let us thank Sylvain again.
Thank you.